This is a computer UPS and this is its transformer. Now, a UPS transformer has an extremely thick output winding, and because of that, this small thing can output up to 100 amps, which can even melt metals. So I thought to myself, why not make a replacement for these expensive induction heating machines used in metal casting? Now I have this leftover metal piece from a previous branch pruner project. So let's make the markings and reuse it for this project. Here I am cutting out two pieces for the contacts. Next comes the point marking on both of them. For drilling a 6.5 mm hole on each of the two pieces. After that, let's clean both the plates to prevent any conductivity problem because of the dust particles. Next, we will need a piece of floor tile because of its high resistance to heat plus high electrical resistance. So let's make the marking and cut it off with my hacksaw. After that, we have to place the contacts on the tile and mark 2 points for drilling two holes of 6.5 mm thickness. It's for fitting these bolts. And now that everything is done, time to assemble everything together. Let's start with the testing part, for which I have to connect the transformer output wires to the bolts. For the input, I am choosing the green and black wires. Let's turn it on and use this metal wire for testing it. As you can see, it's working fine. Now, melting a wire is one thing and casting aluminum is another, because it requires induced heating through graphite crucible, which is a good conductor of electricity and can withstand high temperatures. So let's place the crucible on the contacts and see what happens. The wire started smoking as expected, because producing 100 amperes for a short span is one thing, while handling it continuously is another. And looking at the thickness of the transformer wires, it is no surprise. Now, in my previous video, I made this big transformer using 4 UPS transformers. So if you want to watch the video, link will be available in the pinned comment as well as in the description. So let's connect this transformer's output wires to the contactors, turning it on. Now if I bring my mic closer to the transformer, you can hear the humming sound. The amperes are quite high for this one, so safety should always be first. After that, let's carefully place the crucible on the contacts. If we check the drawn current, it's ranging from 100 amperes to 120 amperes. Although the spark and smoke on terminals indicates loose connections. Whoa! So after correcting them both, the new current is reaching as high as 170 amps, which means that a single transformer is handling more than 40 amperes, which is still high and not recommended. Now let's use this digital thermometer and connect its sensor to the crucible with a clip. If we check the temperature now, we can see that it's rising quickly and has crossed 100 degrees, so this should work. If I add some more transformers and save the existing ones from overloading, now I'm cutting off all the old connectors to prevent any possible heat loss that was occurring initially. After that comes the stripping part, in which I have to keep the wire length same. Next, I'm keeping my two new transformers at the bottom and the previous set on its top. So now I'm going to zip tie all of them together, just as I did to my previous set. Moving on to the wiring of the high voltage 220 volts side, where first I'm connecting the new transformers together and then connecting them to the older set. The chosen input wires, as you can see, are green and black, because this combination can provide us with the minimum output voltage, which is 7 volts. Next, the zip tying part, followed by the necessary taping. Now comes the parallel connection of the output wires, for which I'm using this iron string used in building constructions. There is no specific reason for using them besides bundling. Next, I will use this discarded welding cable that can handle up to 150 amperes. Now, it's extremely important to use a high current copper wire to minimize the voltage drop. Here you can see the way I'm connecting the welding cables to prevent any heat loss that could occur through connectors. Finally, connecting the overall output to the connectors on the tile. And now it's time to test it. So the connections are fine. Now placing the crucible on the contacts. Time to check the drawn current. It is drawing 245 amperes and a single transformer current 40 amps, still high. So now I'm going to use this 2 kilowatts dimmer circuit for reducing the input voltage fed to the transformer and thus limiting the overall output current to 120 amps with a single transformer current to only 20 amps or less. This is important for safety of the transformers. The crucible is still not reaching a temperature that can melt aluminium, and all it is doing is melting some solder and some plastic pieces. That is bad. So let's check the transformer output voltage. It is 3.5 volts AC. Power consumed is only 420 watts, so I can see only three options. First, the secondary winding modification for lower voltage and higher current. Second, increasing the number of transformers until we reach the desired output temperature. And the third, reducing the size of the crucible so that we can easily reach the aluminium melting temperature. Now, I do not have a crucible smaller than this one, but I do have some carbon brushes of different sizes. This one is big, so let's make a crucible with it. Now, I have chosen the third option of smaller crucible and discarded the rest because the project specifically aims at making a crucible heater without any complicated electronics or winding modification so that any one of you can easily make it at home. So here we have it, nice and shiny. Although there's this hole for which I will use this cylindrical brush. So simply inserting it and cutting it. Now let's give this a try. So guys, finally let's place this crucible on the contacts. Let's turn it on. Oh, it is turning red now. Slowly and slowly we are reaching the temperature that we need to melt aluminium. It can melt any time now, and it has started. This is so cool. You see, it's going inside it. That is so cool, man. I think it's filled. See, molten aluminium. So guys, that is all for today's video. See you in the next one. Stay connected. Bye bye. This is a computer UPS transformer. This is the high voltage low current side, while this is the low voltage high current side. On the low current high voltage side, there are 4 wires and we have to choose any 2. So starting with the yellow wire, and here we can see 18.4 ohms. Moving on to the blue one, that is 16.7 ohms. Finally, the green one, 19.9 ohms, the highest. So this is what we are going to choose with the black. Now let's connect the 220 volts home socket supply to the transformer input wires, black and green. Next, connecting the multimeter pinouts to the transformer output. And here I have set it to DC, so setting it to AC,
And here, as you can see, it is showing around 7 volts AC. Now here I'm going to use this 12 volts bulb to show you its performance. See, it's glowing. Now let's cut off the winding cover and proceed further. On close-up, you can see two terminals have double wires. So what I'm going to do is disconnect one wire of one terminal. Yeah, and here we have disconnected this one. After disconnecting the wire, carefully remove the insulation so that we can use it for testing. Doing it from all sides. Done. Similarly, for the second terminal, cut off one of the two wires, same as before, and if you are lucky enough, you will cut off the correct wire. Otherwise, there is one more step that will be required. So I chose a right side wire. Next, connect the 220 volt supply to the transformer input and turn it on. Now comes the part of finding out if I have disconnected the correct wire, and for that, simply short the new cutoff wires. If there is no sparking, then you were lucky. And if I would have cut off this wire, let's check. See, so I was lucky and I disconnected the correct wires. Next, take a copper wire, place it like this and cut it off as shown. After that comes the stripping part. A little more. Yeah. Similarly for the other side. Nice. Next on the main wire as well. And its other side too. Done. Now after completing the stripping on the sides, we have to do the same thing to the middle of the strand. And here it is. Done. Next, place the strand like this and twist it from the sides. Done. Next, take the longer wire and connect it to the center stripped part. Somewhat like this. After that, solder the center tapping point. Finally, connect this 220 volts supply to the transformer input. Done. Turning it on. And now testing the output voltage. First, taking the main terminal as the red one and the new point. And you can see the new voltage is around 7.3 volts. Moving on to the blue one. And we have around 14.7 volts. So this is the new voltage because I have connected the windings in series. Let's move on further. Next, we will need this wooden board for the base and this transformer. Now marking the drilling points. Done. Now let's drill a hole for the installation of the rectifier.
Next, I'm going to use this KBPC 3510 bridge rectifier or AC to DC converter.
Next, connect the red wire from the transformer output to the AC terminal of the rectifier. After that, measure this copper wire, same as the red one, and cut it off according to the length needed. Now, time to strip the tapping wire. Now, this red one was the first AC terminal, so the diagonal opposite is the second. So, place the copper stranded wire the center tap one as shown. Done. Next, I'm going to use these red and yellow wires for the DC output. So let's remove the insulation. Next, soldering the positive red wire to the positive terminal of the rectifier. Yellow wire to the negative terminal. Next, strengthening all the rest joints. Next, I'm going to use this 20 watts DC to DC boost converter because it also has this voltage display that you can control with this potentiometer knob. Although you can use any DC to DC step-up boost converter with a voltage rating between 6 volts input up to 20 volts output. Next, connect the negative wire to the negative and positive to the positive. Done. After that, tight it all up. So this is the close-up for the output side and this is the close-up for the input side, yellow and red wires. Next, I will be using these two wires as the final output. Red is going to be positive and black will be connected to the output negative. Finally, connecting the 220 volt supply to the transformer input and turning the switch on. You can see the display is turned on. Let's zoom in. Now here as you can see that it is flashing 8.4 volts DC output, and if I press this button it is going to flash the input. So it is fluctuating and all we need is the output here, and this is the potentiometer. So let's move up the voltage. Let's move to around 14 volts. That's it. We are done here. So this is my 12 volts, 60 ampere hours, very old battery pack that I made in one of my previous videos. It is lithium ion, and let me show you its voltage. It's only 7.9 volts, so it is very discharged. So let's charge it. Now the battery is lithium ion, so I'm setting my charger voltage to 12 volts so that I can get 4 volts per cell. Next, simply connect the negative wire from the charger output to the battery and similarly positive to the positive wire of the battery, and your battery has started charging. Although my recommendation is going to be something like this, like instead of this boost converter, try using something bigger, like this one is 5 amps. Although I didn't use this one because this did not have a voltage display. Now you people must also be thinking, what is the use of this blue wire that I have spared here that is coming now? Although before moving on to that, I would like to share with you this issue with this boost converter. Now the negative terminal is connected, and once I connect the positive terminal, keep looking at the display there, and you see the display gone. Disconnected and it's on again, connected and it's turned off. Now this does not mean that the battery is not charging when the display goes off, and I will prove that also. Here I have my multimeter connected in the ampere measurement mode. One wire connected like this and the other one, and here you can see that it is drawing around 1.5 amperes. This battery is drawing 1.5 amperes, so the battery is charging even though the display is turned off. Now the next step is to cut off this blue wire and then strip it. Now let's remove this boost converter with a powerful one. So here I'm upgrading my battery charger with this 5 amperes DC to DC buck boost module. This is the input side, as you can see, IN in, and here we have the out. So let's do the connections same as before. Finally connecting the output, and we are done. Here I'm setting the output voltage to 12 volts, same as before. Now let's do all the connections and start the charging, positive to positive and negative to negative. Yeah, and finally it is working. Here you can see that it is drawing around 3.25 amperes, and the voltage has quickly increased to 9 volts DC, and it has to go to as high as 12 volts for full charge. Also, if you want to keep using this boost converter for longer durations, make sure that you add a cooling fan. It will take around an hour because the battery was highly discharged. Next, this is a 100 ohms resistor. I will solder this resistor to this terminal. Next comes this 1N4007 diode. This will be connected to this point. Finally, disconnecting these wires once again. Now take another thin wire and connect its one end to the black output wire that we just disconnected. Next, connecting this black and white wire into the negative slot back as it was before, and the other end of this white wire will be connected to this point. Next, these what you see are two 6 amperes diodes connected in parallel. So the positive side, which is the black side of the diode, will be connected like this, only for one diode. Next, connecting this blue wire from the transformer to the other terminal of the diode. And finally, this last red wire, which is the overall output positive. Now, the reason for adding this blue wire, all these diodes and a resistor is for converting our normal basic charger into the advanced desulfating lead acid battery charger. And note that this charger can no longer be used for the lithium ion battery charging, and if you want to go for that, you will have to remove this additional setup once again, the blue wire, the diodes and this wire. Now if we check the voltage output of this charger, you can see that it is not much different from the previous one because we cannot see the hidden pulses that are coming out from the transformer. Like this meter cannot read it, and not even the most advanced ones can read it, but I'm going to show you that it is actually producing the highest voltage of around 19 volts DC. So for that I'm going to use this 50 volts 5000 microfarad Saracen capacitor. And let's short it first so that there is no charge left, and then finally the other terminal. And here you can see that our new voltage is 18.5 volts, and this high voltage is produced at a current of only 100 milliamperes just to revive a dead battery and not damage it with overcharging. Next, this is my 12 volts Amaron battery. And here I'm going to connect this bulb. See, it is not glowing at all. No sparking, indicating a dead battery. So here what I'm going to do is try to revive it with this pulsating charger. Negative to negative and positive to positive. Let's turn on the charger first and go. Okay, so that's the power coming from the power supply. The battery is still damaged. Now I'm going to leave it for some time like this and then see for final check. So here as you can see that in just 10 minutes the battery has gained enough charge to light up this bulb. Although the bulb is not glowing at its full brightness, but still it is glowing. And if I'm going to leave the battery connected to the charger for around 1 hour or 2, it might even gain half or full charge depending upon the strength that is left in the battery. This, what you see, is a brushless DC motor. You can see the 3 wires for the 3 phases, and this small black wire, this is the neutral wire, which means that the windings are star connected and not delta connected. And you can also see that I've connected this chuck so that you can see its rotation easily. You can see that it's quite smooth, and it's from an old photocopy machine or a Xerox machine. So today in this video I'm going to use this motor and demonstrate its performance with just a single computer UPS transformer, no other component, none at all. This video is just for demonstration so that you can learn, research, and maybe one day add more to it. So here I have connected the brushless motor to the vise, and now that everything is connected, simply choose any of the 2 wires from the 3 phases, not the neutral one, the 3 phases. So I'm choosing the middle one and the lower one, and as I said, right now the switch is turned off. Okay, so everything is fine. Yeah, and now let's turn it on and see what happens. Okay, go. There is humming but no rotation. Now this is just single phase connection and it is not starting. So what we have to do is we have to give it a spin, and that is because right now we are only activating 1 phase. So there is no starting. It is working like an AC motor. So let's turn it on once again and give it a spin. You see, faster. You see that now it is running much faster. Pretty cool. It is running like a single phase AC motor with pretty good torque. See, it is not stopping. Let's say that you want to reverse the rotation. See, reverse rotation. See, it is really difficult to stop. Oh, the torque is extremely high. I can only imagine that if all the 3 phases are active, then the torque is going to be much more stronger. And here, as you can see, that we are getting around 750 rotations per minute. So right. For building an aluminum air battery, the first thing that we need is a battery case that is not easily affected by the electrolyte. Now, these pulley-like things are printed with ABS 3D printer filament, and these are going to house the cathode terminals of the battery, with each pulley representing a single cathode. Here you can see some filament web on some pulley holes, which needs to be cleaned properly before installation. After the cleaning process, it is time for the cathode installation. Here you can see I'm using a long screw plus some XYZ pieces to create a shaft, so that I can connect my pulley to the drill press. This process is going to help me with faster cathode installation. Next, I've hooked in the steel wire, and now it is time to wound it on the pulley. And finally, this is how it looks after completion. Please note that the 3D print design link will be provided in the description. You can check it out. Now here I'm printing a battery case, which is going to contain the cathode, the anode, and the electrolyte. The design looks quite good, although it could have been a little more compact, but anyways, let's move on with this one. Also, please note that this design is not going to work with the PLA filament because that is going to dissolve with the potassium hydroxide electrolyte, whereas the ABS filament is resistant to it. So now that the case is ready, it is time to install all the cathodes in every cell. You can see I'm shaking it and it is not coming out. Next comes the anode, which is the aluminum plate. Here I'm using this magnet to show that it is non-magnetic. Now let's mark the area so that we can cut it out as much as we need without wasting any of it. So I was cutting the aluminum sheet with this sheet cutter, but it got damaged midway. So useless product. The gear broke. Don't buy. Let's use this 6 years old sheet cutter. The plate is a little thicker in size, so it is a little difficult to cut it with my hand scissors. But right now, this is the best I have. Now, let's play some music by the time I complete the anode plates. Finally, now comes the making of the electrolyte. So I have this plastic bottle, well cleaned. Now let's cut it off. Alright, let's keep all this aside. And here we have this small thing. Next, I'm going to pour in 35 ml distilled water in it. 3, 4, 5, 6, 7. This seems a bit less, so let's increase it to 50 ml. Next, I'm going to pour in 5 ml potassium hydroxide in it. Now, let's point my multimeter to 20 volts DC voltage measurement mode. And finally, connect my multimeter pinouts to the battery output terminals, positive to positive and negative to negative. Finally, it is time to pour in the electrolyte. Okay, first cell. Well, single cell is drawing more than 5 ml. Oh, we are close here. So, it is around 7.5 ml per cell. Single cell done. Moving on to the next one. Obviously, there should be 0 volts because the cells are connected in series. And finally, the last cell. Okay, and go. I will see it later. Let's fill in first. And we are done. How much volt are we doing? Oh my god, it is more than 10 volts, 10.2 volts. That is crazy. Cool, right? 10.2 volts battery, much more compact than before, and it did around 4.5 volts. And I said in that video that there was some fault, and this one is working perfectly fine. We are doing here 10.15 volts. Time to test some loads with it. Okay, so here I have this motor fan this time. All right then, let's touch the wires and see what happens. It is working. Wow, that is so cool, man. Oh, my 10 volts fuel cell. Oh, This battery is pretty good, much better than before. It is actually running this big motor. Nice. Okay, now let's, yeah, and I'm also going to show you the type of motor here. DC Swiss motor. Cool, right? Now let's move on with a bigger motor this time, for which I have this 24 volts big motor. It is used in photocopy machines, permanent magnet DC motor once again. And okay, one wire connected, and let's see what happens for the second one. And it is running. Such a big motor and running. Now let's disconnect this one also and move on to an even bigger motor this time. Now this is a much bigger motor, and let's see if it can actually run it at a good enough speed. And even if it does not runs it, it is not going to be a big deal, since the starting current is going to be much higher for this motor. So let's try it anyways and see what happens. And go. Oh, it is even running such a big motor, you see. Yeah, of course it is running at a really slow speed, because this motor is 36 volts and the battery is producing only 10 volts. So yeah, no wonders, the motor is much heavy and the battery is quite light. I've connected this drill bit to it. Now let's do some ampere measurements also. Hope you can see the display. Yeah, right, you can see it. These are the wires, okay, positive to positive and negative to negative. Quick. Oh, I didn't even turn on my multimeter. Moving on to 200 milliamperes once again and see what happens. And go. 160 milliamperes once again. 150, 160. Now what I've seen is that the current is a little lower than the previous one, but the voltage is higher, maybe because I might have just used the power from this battery to run the loads and all. Because when I tried running the motors with my previous video, it did not work. So since this time the motors worked with this battery, so I think that initially the current was higher, but now it has reduced somehow. Yeah, 160 milliamperes, same as before. That's for the steel. Finally, let's connect my LED lights, and there is some important information that I need to share at the end of the video, so don't go away. The battery is going a little towards down, but right now the brightness for a single LED is quite high. Okay, yeah, right. Moving on to my next LED, and this one I think Murphy law is going to get applied. No Murphy law. And this is purple. Moving on to the white one, and here we have it. Cool. Right. Enough to make a small study lamp, right? Oh, that's the blue one. I really hope that you people are enjoying the video. So make sure that you subscribe and support me and hit that like button. And if you really want to go through the chemistry and details for this video, like the very chemistry, you must join the membership. Okay, wrong firing, and oh, now Murphy law. Well, this one is even brighter. You see, the green is seems like the brightest. So bright. It's beautiful. Oh, not great. The short circuit here. See. Now, it is the brightest possible output I have ever had. Beautiful blue LED. See the bubble formation? That's the reaction that is going on right now. It is eating away aluminium. Oh, I can't believe that I had red LED and I was thinking that I've lost it. Maybe I just forgot to test this one. Wow. Now, I was about to tell you something very important. The aluminum air batteries are really good, exceptional. But let's give you a demo here. I'm going to test the voltage once again as I did at the beginning. I've done no change to the battery or the electrolyte. It is same as before, and go. Here you see that the battery voltage has reduced to around 4 volts, which is very bad, really bad. And how did that happen? What's the reason? This is what I'm going to tell you now. So what you just saw was the reduction in the output performance of the cell after some time of use, and that happened because of dendrites formation and passivation. Dendrites form because of the deposition of the aluminum metal on the cathode surface, resulting in uneven structures and thus shorting the entire cell, and so reduced output voltage. While passivation, this happens because of the protective layer formation on the surface of the cathode. It can also occur on the surface of the aluminum plate, which is the anode, but right now I have experienced or researched that this occurs majorly on the cathode if you are using steel. And as my research says, the steel cathode is much more prone to the dendrites and the passivation. So have a happy day, stay safe, bye bye. This is a computer UPS transformer. Now these are thin wires for the high voltage and these are two thick low voltage wires. Now out of these four, I have to choose only two wires with the help of resistance checking through this multimeter. So let's point it to the resistance checking mode. First, take green as common and keep changing the other wires. Here we have 4.9 ohms. 6.5 ohms, way too less. Green and black, 20.5 ohms, that's very high. So none of these. Now taking black as common, and then yellow, 19.3 ohms, very high. Blue, 17.6, and green, around 21 ohms. So blue is, I think, what we need here. It is 17.7 ohms. So let's test the output for black and blue input combination. These two have to be tested. Now setting the multimeter to AC voltage measurement mode, that is DC, F3, and we have AC connecting red to red and black to blue. Well, let's first show you the line voltage. Here we have 235 volts AC. Now let's turn it off and reconnect it as it was before. Time to connect these two wires to the 220 volts point. Turning it on and go. Now, this single transformer is capable of producing up to 100 amperes or more, and because of this, it can easily handle heavy loads. Here, as you can see, that I have 6 transformers connected to each other with the help of zip ties. You see, all zip tied together, and I used this set in one of my previous projects where I made an induction heater. So this is the primary side for all the transformers, and you can see that I have zip tied the green ones, the yellow ones for all the transformers. Now all that we have left are the blue wires and the black wires. So let's strip them. Yeah, so all have been stripped. Time to connect all of them together. So here I'm planning on making 3 sets out of this pack, and each set will contain 2 transformers in total. I understand that I should be using a little thicker wires for the primary side or the high voltage side, because I'm going to use these transformers for welding and the current that is going to be drawn is going to be very high. But this is just a temporary project for experimentation, so go for 2.5 square mm wires or more than that. After completing the taping and the zip tying process, time to move on to the high current secondary. Here, as you can see, there are 12 wires in total, 2 for each transformer, and each denoted by its own color, which is red and blue. Now this color is very important because it is going to separate the wiring process. Now after completing the stripping part, let's move on to the wiring of the secondary. These two will make the first set, these two will make the second set, and these two will make the third set. So take the 2 blue wires of the first set and connect them together with the 2 red wires of the set below. See, now same as before, I'm going to use these iron wires used in construction to join them together. Moving on to the next part, which are these 2 blue wires left out of the second set and these 2 red wires from the lowest set. These will be connected together again. Finally, we are left with 2 blue wires from the lowest set and 2 red wires from the first set at the top. So connecting these 2 together, and same for these 2, and we are done. So by connecting the wires like this, I've connected the first 2 transformers together in parallel, same parallel for the next 2 transformers and parallel for the last 2 transformers, and at the same time I've connected the first set in series with the second and the second in series with the third, and the overall output will appear on the first and the last set wires. Now let's connect the input wires to the home socket supply and hear the humming sound. Turning it on. So let's connect the meter pinouts to measure the overall output voltage. Turning it on. And we have here around 28 volts AC. Now here I have this 1 kilowatts 220 volts high-speed washing machine motor that I'm going to test with my huge transformer setup. Turning it on, holding it from the top because there is going to be jerk, and finally touching this wire. Okay, I cannot believe that it is unable to start even at 27 volts AC. Now here, as you can see, that I have this 12 volts UPS battery, and here with the help of DC source it is going to start. You see? So this is a difference that I just learned. I knew it before that there is going to be a huge difference, but this much, this was not expected. Time to connect the welding cable as shown. Now let's use this iron wire again to connect this top red wire to this welding cable. So the red wire has finally been connected. Moving on to the other one. So the final welding cable has also been connected. Time to do the test.
This is a 4 kilowatts dimmer circuit. If I connect a bulb to its output pinouts and a 220 volts AC source to the input pinouts, then even after turning on the switch, there is no brightness regulation, which means it is damaged. Now, seeing the damaged electronic devices brings no surprise, and we all deal with that in our day-to-day lives. And in majority of the cases, there is no danger. Taking an example of the SMPS power supplies, like the mobile chargers, laptop chargers, printer adapters, or computer supplies, etc. When these get damaged, there is no output voltage or current, and hence not dangerous at all. While in this case, things get reversed. It gives out full uncontrollable power when it gets damaged. It is dangerous because of what I'm going to show you now. Let's say that I have this universal motor connected to its output and I do not know that the device is damaged, and so, as usual, I will set the knob to the minimum and connect the 220 volt supply to the input. Now when I turn the switch on, then instead of the minimum, the motor is going to get the maximum input, which if loosely connected can fall off the table, hit you if you are close to it, or might even short the wire if it moves a distance from its place because of the jerk. So while using it with a high-speed motor, one should be very careful. Moving on to the repairing part. Let's open up the controller casing quickly so that we can analyze the faulty component or components. Now that is the inside view of the controller, although I cannot see any burnt component here. Anyways, so let's open up the rest of the casing so that we can start with the fault testing. For fault test, I will be checking all the components on this PCB. So starting with this potentiometer and pointing the meter to the resistance checking mode. So the potentiometer measurement reads 422 kilo ohms since the controller was set at the minimum. So turning the knob a little bit, and here we have 288 kilo ohms this time. Let's turn the knob further and measure it once more.
This time the resistance is just 5 or 6 ohms, which means it is at the lowest, so it is fine.
Now, the resistances usually go under open circuit. Let's see if they are fine.
4 kilo ohms, 33 kilo ohms, again 33 kilo ohms. So they seem fine. Let's check the fuse here. 3 ohms, it's fine. One more resistance, 4 kilo ohms. Moving on to the continuity check. Starting with the rectifier. This one is a rectifier. Nothing. It's also fine. It's all fine.
Let's do the continuity check on these two capacitors now, starting with the yellow one.
It's fine.
The red one, yeah, fine. Moving on to the small component C321, and I'm not sure what it is, but let's do the continuity check. There is no beep, seems like it is fine. For the final component, we have this BTA 41600P Triac. So let's check if it is under short circuit.
These three are the terminals. Okay. Oops. This one is under short circuit. This is fine. This is also fine.
Seems like our Triac is damaged.
Now I have another new Triac, and if we do the continuity testing on this one, you can see there is no beep, which means that was under short circuit and dead. So let's replace it. Please note that for deeper knowledge on these topics and some really crucial key points, make sure that you join my patrons page that I have just started, with which you will know the project that I'm working on right now. Plus, when it is released, it will be available first on Patreon and then on YouTube. Plus, it will be ad free. Also, there will be video clips to help you improve your understanding of the project and pointers that you won't find anywhere else. Plus, a lot more perks, which you can read on my page. Link is in the description and comment section. So, coming back to the topic, after replacing the Triac and assembling all the parts of the controller back as it was before, it's time to connect the wires. So first, I'm connecting the bulb holder to the output pinouts and then 220 volts AC source to the input pins. After that, it is time to test it. Working nice and smooth. This is a microwave transformer, and as you can see, it has been modified. Now many a times we need to run our 110 volts appliances and we have 220 volts AC from our home socket. So in that case, this modification helps because it is a step down transformer which converts it to 110 volts AC. But it has been lying around for many months, so I thought about reusing it in my upcoming project. Here, as you can see, that I've cut off the transformer core to carry out the modification without damaging the windings, which can still be used in the future, and these are really valuable. Next, the primary needs no modification, so leave it alone. Next, this what you see is a dead-end discarded DC motor armature, and I thought about reusing its armature winding to create the thick secondary winding. And this is something that I have always wanted to try, and the time has come. Please note that the different gauge sizes of the armature winding is not going to create any problem, since all of them are being connected in parallel. And make sure that you only use the copper windings. So anyways, moving on with the construction part, connect all the windings in parallel. Next, connect one end of this thick wire to the vise as shown. After that, trim the other end for equal size. Next, place it in the chuck of your cordless drill. Now, turn on your drill until your wire is strong and rigid. Next comes the insulation removal part as shown, since these are enameled copper wires with high temperature insulation. So for that, I'm using this butane gas which is going to melt away the enamel, leaving behind only its residue, which again needs to be cleaned properly with the help of a sandpaper. After completing this, simply trim the ends as shown. Now, this is a big bolt, and once again I have modified it to carry out this unique process of soldering the ends evenly, and it works really good, as you can see. And here we go, we now have a thick new secondary which now needs some insulation, for which I'm using this high temperature winding sheet and some electric tape. And make sure that it is very tight. It turned out pretty good, right? So here, as you can see, that I've cut off some U shapes to separate the primary and the secondary winding as shown. So the new transformer with the new voltage and current ratings is almost ready, and all that is left is to do the welding of the core to complete the magnetic circuit. Here, as you can see, that I'm giving 3 arc welds on each side, and there is an important reason behind that which I will be telling you later. Next comes the weld cleanup process, and then starting with the test. Here, as you can see, that I'm connecting it to the mains. Turning it on. Oh, it has started smoking. Seems like there is something wrong with the windings. Once again, and this time let's short the secondary. Here you can see that it is definitely working, but I think the primary is damaged. So after taking out the secondary, we can clearly see the damaged part. It could be because I did cover the transformer windings before performing the arc welding, and somehow some arc might have shorted it. So anyways, I luckily have a microwave oven from which I'm planning to salvage a new microwave transformer. If you look closely, you can see the transformer at the bottom, although it has a lot more components which can be useful for me in the future. So anyways, let's focus on the transformer and take it out. So here we have our new transformer, and it looks fine. Also, here I'm showing you this core welding area, which I personally do not like because it shorts up the silicon steel core and thus reducing the overall transformer efficiency. So I'm not sure why these companies go for the welding process of these transformer cores. Anyways, let's strip the transformer winding wires so that we can move on with the testing part of this transformer. Please note that this transformer can output up to 2000 volts AC with 1 amps output current, which is extremely dangerous and can definitely kill anyone. Here you can see the arc length of the output windings. It is phenomenal. So try not doing it at home. Now, after cutting off the core, we can have a closer look on the new primary. It is new and shiny. Here you can see that I'm using this toothbrush to hammer this winding safely and move it to the bottom. Now here is some additional core that comes pre-installed with the transformer, so I'm placing it back as it was before. And finally, let's mount the secondary once again and hope that it works this time without any problem. Although this transformer feels a little smaller than it was before, but the windings fit same as the previous one. So this time I'm carrying out all the winding protection, as you can see. It's a great loss that I've destroyed my previous transformer with some silly mistake, which could have easily been avoided. Anyways, I'm giving only 3 welds on each side to reduce core losses. Next comes some strong terminal making for secondary endpoints. And finally, it is time to do the test. There, as you can see, that it is working pretty good. So many amperes. Now let's do some ampere tests to see if I'm reaching around 500 amperes as you people chose in the community polls. So the maximum current that we reached was around 481 amperes AC, which should be more than enough for melting the aluminium pieces. Let's move on with the AC voltage test, which is no longer dangerous now as it was before. And as you can see, that my transformer is putting out around 2.7 volts AC, which is good enough for me. So let's move on with the making of the crucible heating plate. Now this is the very same plate which I used in my previous project, where I used some UPS transformers instead of this one microwave transformer. Now this is a mini crucible that I've made from a big carbon brush. Now let's put in some aluminum pieces and turn on the transformer. And at the same time, I'm also measuring the amperes drawn. The drawn amperes, as you can see, are increasing and closing at around 100. Plus, it has easily melted all the aluminum inside it. So this is definitely a cheap replacement for an induction heating machine for casting purposes. Although the size of my crucible is quite small and I cannot place a big crucible instead of this one until I've made a proper cooling system for this transformer, because it is going to be turned on for longer durations until we are done with the melting process. And this high transformer temperature will have a really bad impact on the winding insulation. So once we have placed some big PC cooling fans to cool up the windings, I think we can then move on to a bigger crucible. But until then, I hope you are satisfied with this experiment and happy with the results. Also, please note that I have carried out a similar experiment with some UPS transformers. So if you haven't watched that experiment, please go to the link provided in the description. So here, as you can see, that the casting is complete, and I tried giving this molten aluminium the shape of a bolt. It looks quite similar to it, especially from the edges, but without any hollow threads. Also, make sure to share my video with your friends and colleagues so that they can join my channel same as you. And to further support my work, make sure to hit like and join my membership. Please note that I have started these quizzes and community polls so that you can learn new things every day, plus choose the next upcoming project that you want from the list. The highest votes will get their project selected. With that being said, stay safe. Bye bye.
This is a computer UPS with a switching circuit and a transformer. If we give it 12 volts input, it gives out 220 volts. Now, after taking out the transformer, if we connect it in reverse, we can get an output of around 7 volts AC. Fine, but let's check the amperes because that is the sparky part. See? So here I have connected my clamp meter. Oh man, 40 amps. Yeah. Now, instead of a single transformer, I'm going to use 4 transformers together. I've also made these 2 metal connectors to connect the output of these transformers in parallel, and these connectors are from a discarded metal piece. One of the greatest reasons why I never throw away stuff. They can be useful anytime. To the first connector, I will be connecting the red wires. So all have been connected. Moving on to the blue ones. So here I am zip tying all the transformers together because it's the easier way to do it. Now let's connect the input wires in parallel, green to green and black to black. Green and black. Transformer is almost ready, and here I've used this old discarded mouse cable to make this big transformer handle because it is quite heavy now. So here I'm going to use these 2 yellow and black wires to connect them to the high voltage side, which are bundled together as green and black at the back of my transformer. For the output, I have these 200 amps wires from an old inverter battery. It is finally complete. Now here I'm going to use my series bulb to do the safety check first. So take one wire from the bulb and one from the transformer input and join them together. Now take the remaining 2 wires and connect them to your 220 volts home socket supply. Turning it on, the bulb is glowing dim, indicating that everything is fine. Anything else would indicate either improper connection or short circuit. So testing it with the same wire again, and this time the current is going to be very high. Extremely high current. 4 times. Oh, oh man. Oh, that was extremely dangerous. So you can see such a high current that we can get out from 4 transformers when connected in parallel together. So for the second experiment, I was thinking about using this. It is a spring and I have stretched it. So using it to heat this up and then in turn heat water with it. Let's dip it here. And here it is, rising quickly. 30 degrees. 40 degrees. 90 degrees. Oh my god.
We are reaching around 98 degrees. Let's turn it off. So now I'm going to use these two nails and try and weld them together. So it's on, and now I'm going to touch them. Oh. Oh. Wow. That is crazy. The current was so high that it could actually melt the tips and weld them together. After doing all these experiments, I got a little curious for finding out the maximum temperature that we can achieve through short circuiting this spoon. So here I have two vices that are holding the spoon. Next, I'm connecting this red wire to one end of the spoon. After that, we have to connect the sensor of the digital thermometer to the center of the spoon. Time to short circuit the wires. Wow. Oh man, the wire is not going to survive this.
Just a quick touch.
Oh man, it was 228 amps. So finally I have doubled up the wires to increase the current handling capability. Let's start the test. Oh. Oh. 270 amperes. The amperes are way too high because of the increased wire thickness. These wires, the transformer wires, cannot handle that much current. They will burn out. Now the spoon was taking a lot of current, so I had no other choice but to replace it with this spring. So let's measure the short circuit temperature. The temperature must be rising. Let me see how much the temperature is. 80 degrees. It's unable to measure beyond 100 degrees. Repeating the test with another multimeter of mine. Let's hope that this one at least gives me the proper maximum reading. Let's short circuit it from here. Whoa. That is so bright, man. It's melting. Oh. Now I have this long screw with a damaged head, and I have this power window motor. So I thought about fusing the two of them together to elongate the shaft of the motor. Oh, scary. Off, 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 off. Whoa. Okay, careful. Oh, now we have a long shaft motor. So cool. It's all wobbly. But yes, it welded. So cool. Now I have the silicon steel from a transformer, and I was thinking about finding out the drawn current. Oh. Oh. How much is it? Oh my god. Shit, man. Oh crap. And go. Oh. Oh man. Oh, that is so bright. Oh, that is so cool. It was so stupid of me since I forgot to switch it from DC to AC mode since I have not connected any rectifier. So now I'm going to use this silicon steel. It is from another transformer, different kind. Go. Oh. Wow. How many amps is it? It looks so cool and very hot, man. Whoa! It is red hot. That is so cool. Oh my god. Oh, it's not coming out. So how many amps was it? So let's check. Now you can further increase the amperes by adding more such transformers in parallel depending upon your requirement. Now there is this curious thing to note. While the transformer was on, the maximum water temperature was only 98 degrees. But as soon as I turned it off, it went to as high as 99.8 degrees, which is close to 100 degrees. Why is that? Let me know in the comment section. So these what you see are some propellers, 11 inches, 12 inches and 14 inches. In my previous video, I made this 15,000 RPM DC motor using some gears. And in that video, I told you that I was going to test to find out which propeller is going to make it fly. So here I have different sizes and I'm going to try that now. So first I'm going to connect this 11 inches propeller. So everything has been connected and here I'm using this 24 volts 20 amps power supply and go. Now here I have this controller with which I'm going to control the speed of the propeller. So the lift was better than before, but still it could not fly. So here I'm going to switch it with this 12 inches propeller. So even the 12 inches propeller is unable to lift it at full power. So here I have finally connected the 14 inches propeller. It is time to turn it on and go. As you saw that none of the propellers could produce enough thrust to lift up the motor because of the added weight. This is the wire. Let's move it like this so that you can see and go. Oh my god, it is charging my cell phone. My green LED. Oops. Water is coming down. So starting with the construction of a single cell of an aluminium air battery, here I'm using a plastic cup, ABS and potassium hydroxide solution. Now this is a graphite piece or carbon brush used in motors, usually DC motors or universal motors, and as I have done this previously, here I'm using it again as cathode and I have connected that cathode to the positive terminal of my multimeter. Now to the negative terminal of my multimeter, I have connected this small aluminum piece and here I have dipped it in the same electrolytic solution, and you can see the display voltage. It is rising and at some point it is going to stabilize. I want to do a comparison here between two different types of cathodes. And here you can see that it is generating around 1.6 volts DC, which is very good. For the current measurement, I'm using this multimeter. Let's point it to 200 milliampere current measurement mode. Okay. Same aluminum sheet. Done. And now this is the problem that I've been facing for so long. Like initially the current is very high, but after I leave it for some time, the current reduces. Now this is because of the oxidation layer that is forming on the cathode, which is the carbon brush here. Now let's disconnect the carbon brush and instead connect something else, which is this steel wire that I have. Let's try this one this time. Here you can see that the current is much better. We are doing like 3 times more than the previous case. Now let me show you something beautiful here. Initially I used this small aluminum sheet, right? Now instead of this, what will happen if I use this big sheet? So to see that, let's fold it and then dip it inside the electrolyte. So here, as you can see, that the current has increased, and now because the oxidation layer is getting formed, the short circuit current has started to reduce. So anyways, let's start building a big aluminum air battery by using a case of a dead old lead acid battery from an old motorbike. Now here I've installed all the steel plates, as you can see, and these are the aluminum plates, and I've installed one of the plates, the aluminum ones. So the method is to connect the first steel plate to the second aluminum plate, and similarly the second steel plate to the next third aluminum plate, and so on. The first one will remain disconnected because it is going to be the overall output. So all the aluminum plates have been placed inside, and there is a good enough gap to prevent any possible short circuit. Now let's screw them up. So here I've connected the steel and aluminum plates in series combination. As you can see, it looks beautiful. Now this terminal that you see is going to be the final output, and the second one is yet to be connected. So let's finally connect the last one. And here I'm going to connect this wire as the final output. Now I understand that this battery could have been made much more compact, but I did not have the perfect material, and right now I don't have the time to make a 3D printed model, so I used this battery instead. It was discarded and available. Yeah, seems nice. So the battery construction is finally complete, and all that is left is to check all the connections, and after that simply pour in the electrolyte, which is the same potassium hydroxide. Let's do that. So let's do the continuity check first. One wire to the mains and the other to the aluminum plate. Next, this one and the aluminum plate, this one and the next plate, correct. Next this one, finally this one, perfect. So guys, now comes the most important part. Let's add distilled water to this battery. Now it is time to connect the meter pinouts to the battery terminals. Black to the negative and red to the positive. Battery has been connected, and now it is time to point the meter to 200 milliamps current measurement mode. Now let's start pouring 5 ml only. The meter is not going to show anything until I have filled every single cell, but that is just a negligible current, 0.2. Proper current will be seen only after I've filled all the cells properly. And finally, the last one. Let's see what happens, and go. Oh my god! Oh, it has crossed 200. Yeah, sorry, let's do 10 amperes and see how much current we are doing here. 0.2 for 240 milliamperes. That is so cool, man. Now there is no pH stabilizer at present inside the battery, and it is going to oxidize really soon, but you can see the maximum amount of current that I have produced, yet it is 240 milliamps. It was, and now it is 220, but still it is quite good because it is also under short circuit. Now that this test is complete, let's quickly move on to the voltage test. Positive to positive, negative to negative. How much is it? Voltage is 4.186 volts. There is something that is not just right with the battery. I had hoped for more voltage. I don't know why I'm getting less volts. Let's check cell by cell voltage and then we will know everything for sure. Oh, here I'm getting only 0.7 volts. 0.3, 2, 0.7. Voltage is less. I think there could be some possible contamination. I only had this much potassium hydroxide, so I will have to buy more for conducting more tests. But sure, let's try running some actual loads with it and see how it performs. We have the lights glowing pretty good. Cool, right? Now, this is a circuit that I've got from DF Robot, and this can convert even 0.5 volts, like boost it up and charge your cell phone. So let's try this one. If you want to buy this, link will be provided in the description, of course. Let's see if I can charge my phone at least. And it is on. See, the indicator is glowing here. Now it is time to connect my USB cable. And now I need a cell phone. This is the wire. Let's move it like this so that you can see, and go. Oh my god, it is charging my cell phone 82% and charger connected. Now let's turn off the lights further. That is so cool. Although I'm a little disappointed because the battery didn't produce the desired voltage, but I did learn a few things, that we have to be very careful with the handling of the electrolyte. If it is contaminated or something happens to it, then it is not going to perform as expected, because it is quite obvious that a single cell produced around 1.6 volts, so 6 cells should produce around 9.5 volts, and it produced only half in total. This is, which one is this? Oh, this one is red light. This one is beautiful too. Yeah, it is a battery for sure. It's nice and everything, but there is a lesson in everything. I cannot find the green and the blue one. I believe one of these should be the one. Yeah, that's the blue LED, my blue LED. You see? And, and this one should be the green. See? My green LED. Oops. Water is coming down. Sorry, the electrolyte. So guys, I think I figured out the reason why the battery did not perform as expected, and that is because there is a good possibility that some particles or some deposits of sulfuric acid might still be remaining inside the battery, and because of which the sulfuric acid reacted with the potassium hydroxide and tried to neutralize it, which means that I can no longer use an old battery case for this kind of project. I need a really new plastic case that has never been in contact with any kind of chemicals. Here I have this small motor from an old DVD drive. Let's try and run this. So it is running, but I am a little disappointed because I had hoped to run a much bigger motor with this battery, and I was way too confident that it was going to work. And I never thought that this could be one of the reasons because of which my battery might not work. Because what else could be the reason, since I tried a single cell and it produced around 1.6 volts. So it should have produced around 9.6 volts. So that's it. See you in the next one. Bye bye. Now, before proceeding any further with the construction of this DC power supply, it is important to test it. See, so the power supply is working, and now it is time to test the output voltage. And here we have 13 volts AC, which is good. Now the capacitor that I will be using here will be 40 volts DC and a 7100 microfarad. So finally our portable high current power supply is fully complete. It can handle a maximum up to 400 amperes peak. So let's test it. Working pretty good. Here we have a 24 volts motor. The voltage is high, so the RPM is going to be a little low, but starting torque is going to be very high. Nice. Moving on to one of the most high current motors, 32 amperes, Nidec, 12 volts. This is going to create a lot of spark, so I have to be careful. Oh, once again. Oh man. Let's try it now. What? See the amperes? I really got scared. This time I'm going to hold it really strong. You see? So high current. Such a high current motor running with this power supply. That is just great. Oh. Now moving on to the highest current bike starter motor, and oh, see. Oh, extremely high current power supply working so nice. Feels like a racing bike. Also, for all my platinum members here on YouTube and my Patreon members, I've made a separate video with all the detailed instructions and safety precautions. They can watch it and build this power supply if they want to, because that video is going to be very helpful for those who actually want to build it. And if you are not a member yet, you can try it for a month. If you don't like it, you can always leave. So that's all for today's video. Thank you so much for watching it. Take care. Bye bye. Why is motor sparking a major issue in high-speed machines? To answer this question and give you its solution, I will be salvaging a motor from a vacuum cleaner with similar issues. Time to open the filter. Let's put some WD-40 into the screw slots. The thing is that these screws are really tight. Like, even after placing WD-40, they are still not coming out easily. I can see the motor now. Oh, the first one is out. Last one. Finally. This is a universal motor and it's from a vacuum cleaner, as you already know. This is the suction side, and at the back, as you can see, is the cooling fan. So there are a number of plates for cooling up the armature and the stator windings, because it gets really hot since it is designed to run at 15 to 20,000 RPM. Now this is my 24 volts DC power supply variable, and I'm going to use this power supply to test this universal motor. So here I'm giving you a close up on the connections. Moving on to the next one, and oh. So guys, to be 100% sure for the question if this motor is actually working or not, I will have to test it on 240 volts AC home socket supply. After so much safety, I'm still scared. Okay. Whoa. It is working. You saw sparking once again. Whoa. So the armature is getting shorted at such a high voltage, which means there is definitely some huge problem with the motor, which I will have to solve. Whoa. See, so much spark.
So let's open it further and look for the problem. Now guys, if you have a closer look at the motor, you can see the stator and the rotor. Everything is so neat and shiny and robust. Let's open it further.
So here is the close-up on the cooling fan. Looks nice and shiny. Finally, let's remove the brush slots. Wow. Seems like there is a broken edge.
Now, on close inspection, it's clear that the commutator bars are in bad shape. So, for repairing it, I searched this problem on YouTube and found some videos in which it was shown that by simply cleaning up the commutator surface and the in-between areas of the commutator bars, they solved the sparking problem easily. So, let's try that. Next, in some videos we can also see them cleaning up the brush surfaces, so here I'm doing that too. And now, after completing all of that, it's finally time to assemble the motor back as it was before for testing it.
So I've completed all the connections and the assembly is also complete. Finally, it is time to test it. Okay?
The result is clear, it didn't work at all. Since a lot of videos on YouTube are only for monetization purpose with no thought to the precious time of their audience. So anyways, here you can see that I'm cutting out a portion of my motor surface to show you a better inside view of what is happening. Time to run it again.
Okay. Now, this problem is not because of the simple dirt accumulation on the commutator bars or in between it, but because of the shorting armature windings. This usually occurs because of the insulation breakdown, and there are many reasons for it. Number 1, overheating despite of the presence of the cooling fan. Number 2, mechanical stress that can occur because of the physical vibrations that are faced by the armature winding when it is rotating at high speed. Number 3, electrical high voltage spikes and surges can also break down your winding insulation. Number 4, the age of your motor, because the winding insulations can go bad over time naturally. Lastly, number 5, moisture or chemical exposures can also be the reason for it. Now, time to practically prove it here.
Please note that minor sparking is not considered a problem. Now here is the top part of my vacuum cleaner, and on the label, as you can see, it says 1000 watts. The home socket voltage, as you can see, is around 240 to 250 volts AC. Now considering the power factor as 0.9, the maximum possible current should be 4 to 4.5 amperes AC.
Now let's test the actual current that it is drawing right now. And as you can see that it is drawing more than double, and that too when it is not loaded. Also, this double current indicates twice more power consumption, thus making it a 2000 watts motor instead of the initial 1000 watts. So where is this extra power going? And the damage I showed you on my carbon brush earlier, that was also because the armature was drawing more than double the current, so the brushes were under excessive heating pressure which they could not handle. So this type of problem cannot be simply solved by sandpaper, and the only true solution is to replace the armature or rewind it. And this will be covered in my next video if you people take an interest in this one. Now, there's this important announcement. I've started these daily quizzes to refresh your knowledge on engineering topics like motors, generators, electronics, etc. And it feels really good to see you all participating so much actively in it. And well done to all those who have given correct answers. Please note that if some of you have still not received any quiz notification from me, make sure that you have subscribed my channel and have turned on all notifications, and therefore check out where you stand. Also, in total, I have 3 channels now. The first one is my main Mr. Electron channel. The second one is the Mr. Electron Alternator channel. And the third one is my Mr. Electron Hindi channel that I have just started. So if you are a Hindi viewer, make sure that you go and subscribe. On top of all this, I've also launched my patrons membership page, which means that from now on, if you have queries or you want to take a deeper dive into the topic that I cover through my videos, then this page is for you. So make sure that you check out its membership box. Although you can also become my member here on YouTube for all my channels by simply clicking on the join button. Next is my WhatsApp channel, which is going to combine the content for all my channels on a single platform. So make sure that you try it now. Bye bye. Let's test the torque this motor offers. Here is this metal piece and go. Three transformers is all I need to run this brushless motor. For plan A, I've connected the primaries in parallel. For the secondaries, let's try delta connection. And we have 3 output wires representing the 3-phase delta. Now let's quickly give 220 volt supply to these transformers to check if everything is fine before the final testing with the motor. Turning it on, go! Oh. I always knew that the delta connection was not going to work. I was just testing it. The actual connection is the star connection. Let's do that. For the 3-phase star connection, I'm choosing the red wire to create the neutral point. Finally, we have the blue ones as the 3-phase output wires. Turning it on and go! Nothing happened. It's fine. Which means now it is time to connect this beauty. So as you can see here, I've placed the motor on the vise, the brushless motor, and finally it is time to connect the blue wires from the transformer to the green wires of the brushless motor. Turning it on and go! It's not working. Yeah, it has started the magnetic locking. Seems like I can also try this small black wire, which is the neutral wire, and connect it to the neutral point of this transformer, the red wire. Right now the switch is turned off and turning it on. Go. Go. The motor also did not turn. Let's give it a go once again and quickly try to turn it. Okay, and go. Oh, okay. Why isn't anything working today? Oh, now I get it, and no wonder it is not working. Even though I've connected the output of the transformer wires in 3-phase format, I still have not given it any phase shift, because of which there is no rotating magnetic field, and so the motor is not working. Now to create a phase shift, I'm going to use this discarded fan capacitor. I'm going to start with the star connection. This looks tight. This one, yeah, this is loose. So we are going to have this black as common point, and these are going to be the three-phase input wires, the green ones. And for the capacitor, let's choose two of the transformers and connect the green wires like this, and these 2 points are going to be connected to the 220 volt supply. Okay, so starting with the connections of the brushless motor with the transformer output wires, and finally connecting the input side to the 220 volts mains, turning it on and go. Yeah, there is some vibration. Okay, now let's try and spin it after turning it on. Okay, go. Let's spin it first and then turn it on. Okay, wow. That was cool. Let's check the torque. It is losing its torque really fast. Now I have this 220 volts AC capacitor, so let's place this one instead of the fan capacitor. Finally, let's turn it on and see what happens. Okay, go. Oh, there's too much vibration. Let's do the same thing, turn it as soon as I turn it on. Once again. Not working. Now let's spin it and then turn it on. Whoa! Now it is working. Really bad torque. As soon as I touch it, I even touch it and it stops. Now for the last try, the secondary remains star connected, while for the primary high voltage side, I'm going to connect it to delta, for which the black wire of first transformer will be connected to the green wire of the next transformer, and then black wire of the next transformer will be connected to the green wire of the last transformer, and after that the remaining two wires. Next, to give a phase shift, I'm going to use this same capacitor that I used for star. So take any two of the phases and connect the capacitor as shown, and these two will be connected to the 220 volt supply. Now, before connecting this setup to the mains, I would highly recommend you to add this 220 volts 100 watts bulb in series with the transformers, so that if anything goes wrong, all that is going to happen is this bulb glowing a little more brighter than before, and so it is going to keep your circuit, your machine and everything safe. Okay, so guys, turning it on, delta connection at the primary, and go. You see the bulb is glowing and the motor is not running, and if I give it a spin, because there is a lot of vibration, it is running. That is so cool. And you can see that the brightness changes when I touch the motor. So I'm going to use this steel. Oh, it stopped. Once again. Much better torque than before, and you can see the brightness changing. Now, you see this torque, it is still stopping. So to improve that torque, we can add more bulbs in series to increase the current flow through the transformer, and then more current to the motor. So here I'm adding 3 bulbs in series to increase the current flow, and one bulb is 100 watts and these two are only 60 watts. So 220 watts bulbs. Now let's turn it on and see what happens. Okay, and go. Too much current. Again. Yeah. Vibration. All the bulbs are glowing. And the motor is running. Once again, and in the reverse direction. Let's try and stop it with this metal piece. Unstoppable. Yeah, you see the difference? I have fed around twice more current, almost twice more current, and you can see the improvement in the torque. This entire piece, the motor piece, has begun to shine. And imagine if I add more power, like more bulbs, and then give more power through the transformer and to the motor, results could be exceptional. So this method is just for experimenting, like it has no practical applications yet, unless we find out a way, like something that is going to give it self-starting plus even higher torque and more RPM, then we can achieve that. But right now this is what I can offer you, like a higher level of torque. So guys, that's all for today's video. I hope you enjoyed it. And always remember that both positive and negative feedbacks are welcome on my channel, so that I can understand if I'm going in the right direction or if I have to do certain changes. So that's all for today's video. Thank you so much for watching it. Bye bye. Do not use soft drinks to restore any dead battery. More details later. Follow the steps carefully and always remember that the project is dangerous. So here, as you can see, that the drawn power or charging current has started increasing little by little, and soon this battery is going to consume a lot of power from this supply. It will take a lot of time. The power drawn might go down and might as well go up. You have to leave it for long duration, maybe 24 hours at this value, and then it is definitely going to retain its power. And make sure that the place where you are reviving your battery or charging it is well ventilated, because while charging it is going to emit hydrogen fumes. Now, the problem with the soft drinks is that they cannot remove the sulfate deposition on the battery plates. Furthermore, the added sugar in the cold drinks is going to spoil the chemistry of the battery, which is ultimately going to depreciate its performance. So make sure that you use baking soda instead. So guys, now that our battery has revived, I'm going to conduct several tests here, starting with the open circuit voltage measurement for the battery. And here we have around 12.22 volts, which is nice. Now the second one is this 55 watts 12 volts bulb that I connected at the beginning and it did not work. So let's try it this time and see what happens. See how bright it is glowing. So yeah, it is actually working. And the third test is the voltage drop. So let's connect the bulb and the meter together to check the drop on the meter screen, and go. And here we have 11.8586 volts, which is very good. It is dropping, of course, because the bulb is consuming power, but still it is not dropping to absurd levels, which is a great sign. And on top of it, I did not charge this battery to full because it is supposed to be charged at 14.4 volts, but I did only to 13.6. Let's test it once again, just for brightness checking. And you see, oh, pretty good. So the baking powder formula actually works. Now here I have this 12 volts 22 amperes permanent magnet DC motor. So let's test this one. Thrust is very high. Oh. Nice. Also guys, I have this new machine that is going to be added to my lab equipment, and I can't wait to show you guys what is inside and how it performs. So stay connected because it is amazing. Now you already know about the SD card. This is the card reader that we get with it. Next, as you can see, the card reader is here, so it is not connected to this microscope. Now I'm going to show you something really cool. This is another stand for the lights where you can connect these slides that are given to you for experimenting and fun. This is the PowerPoint for it. Done. Moving on to the next part, which is my laptop. And here I've connected the USB cable. Now let's turn off the lights for better view. Here it is showing us two options. One is mass storage and the other one is PC camera. So with the help of this remote, I'm going to select PC camera. And you can see the display is gone. And now my laptop is going to act as the display for this microscope. So we have to go in the search bar and search for camera. Next, here you can see, yeah, that's the honeybee wing. So this is how it looks, and let's zoom it because it is not zoomed right now. So a little more adjusting. Yeah, much better now, right? And we can move this piece like this. See? So the best thing with this laptop view is that you have the record button directly from here, so you do not need this SD card. And this white button that you see, that is the record button. So you can record it directly from here or take snapshots from the button below. And here you can see stop taking the video or pause the video, the pause button and everything. So this is how it is going to help you, like you can work on your microscope and side by side record your work as well, plus watch whatever you are doing on really big screen. Plus this is all in 4K and the camera quality is much better than the previous ones. So it is an excellent recommendation. Moving on to the next features of this one.